I want to kind of really talk about what I mean by the formulas are consistent, and I want to kind of show you at least a simple example of that. Okay. And so then what we'll take a look at as an example is we're going to take a look at Newton's second law. Which if you've had some physics before, then you'll know that this is a fairly important formula for us. Now what we get is that it talks about the fact that the net force is equal to the mass times the acceleration. Okay. And so what you can see is that this symbol here, this is a capital Greek letter. This is sigma. And what you get is that this symbol is interpreted as to add. So just like the delta means the change in or the difference of, sigma means to add. And so what you're doing is you're adding up all of our forces. And so then what you get is that the sum is going to be your net force or the total force. Okay. Now you'll notice that there's an extra line on this F and that there's an extra line on this A, but there's not an extra line on that M. And that's important because what you get is the extra line in the notation indicates that these are vector quantities. And the important thing about vector quantities, which we're going to learn about Tuesday, I think, is that vectors essentially have a direction. And this is one way to indicate that with a notation. The other option you have is to draw little arrows above the symbols, and that one's pretty common, but it's one I don't like. So it's not my favorite. And then what we have is this M that does not have the extra line, then that implies that it's a scalar quantity. And all that means is that there's just a value, there's no direction. So what you're seeing is that how we write the symbols carries a lot of information in terms of when we look at our formulas, okay? But I can write down that the M here, this stands for the mass. And this A here stands for the acceleration. So what you get is the mass times the acceleration is the net force or the total force acting on the object, okay? And so that's enough for the moment. So this is our formula. And then what I want to go in and talk about is that when we do these little brackets and we have something inside the brackets, then what this means, we're going to interpret this as the units of whatever we put into the brackets. Okay. It can also be done that the brackets tell you the physical dimensions like length times mass or, length over time or, whatever kind of things. But we're going to do units is the way we're going to interpret that. I think that's a better way to go at this stage. How do I fix this? There we go. Sorry. Yeah. And so now what we're going to do is we're going to go in and take a look at our using SI units, we're going to take the units of our net force. And what you're going to find is that those are the units of the mass times the units of the acceleration. Okay. And so what we get is the units, the SI units for mass are going to be the kilogram. And then an acceleration we're going to find out in chapter 2 is going to be a length per time squared. So in the SI units, it'll be meters per second squared. And what you get is this particular combination of base units in the SI system are the derived unit called a Newton, which is the unit of force. Oops. The thing is that the name of the unit is not a proper noun, even though it's named after a person. It's the name of the unit is not a proper noun. So no capitalization on the name of the unit. Okay. And so as I mentioned, this is a derived unit. And it's built up of this combination of base units. Okay. And so if we change systems and we go into the Gaussian system or the CGS system, and we look at our, units of the net force, which should be equal to the units of mass times the units of acceleration, then what we're going to get is that mass was in grams and acceleration is in length per time squared, so centimeters per second squared. And this particular combination of base units in the Gaussian system of units is a derived unit called a dyne. You'll notice there's no symbol for the dyne. Well, that usually speaks volumes to me. That means we aren't going to be using it a lot, because if we used it a lot, there'd be a symbol for it. So, but again, this is another derived unit. And so this is what I mean by being consistent. As long as every value in the equation goes in SI units, my answer will come out in SI units. You don't necessarily have to track the units. Okay. But if we try this with our metric system of units, then what you get is that while it will be dimensionally correct, we'll have the correct physical dimensions for the units of a force, we won't get a derived unit. Okay. And this is the point. So when we look at mass, it will be in grams, and an acceleration will be a length per time squared. So that'll be in meters per second squared. And what you get is that this has the correct units of a mass times a length per time squared. That is the dimensions of a force. This is not a derived unit. It's not a Newton. It's not a dyne. It's not a something else. I mean, it's not technically wrong, but it's not useful.
I have a question.
Yep.
So is it the sigma symbol next to like if, like if?
That's not an I, that's a second line on the F, indicating it's a vector. So the
Got
F
you.
has an extra line on it, just like the A has an extra line on it. This particular notation is called blackboard bold. Okay. And so you'd write an A with an extra line, an A with an extra line, a B with an extra line, a B with an extra line. C's with extra lines look a little funny. D with an extra line. And then what'll happen is, in the notation I use, this will indicate that these quantities are vector quantities and therefore have directions. And if they don't have extra lines, then that implies they're scalars and do not have a direction.
Sir,
Yes.
is it compulsion to make extra dash? Or can we just keep the arrow instead
You
of
can
that?
keep the arrow. That's fine.
Okay,
I read
thank
it just fine. I just don't like to write it.
you. Okay, thank
Okay.
you.
Yep. Yep.
Okay.
There are two camps. There's either those that do bold to indicate their vectors or those that do arrows. What you'll notice in our book is that they took the middle of the road, so they made it bold with an arrow, so everybody's equally unhappy with the notation. So, I like the bold. Then I like the extra line on the symbol because it writes faster than doing the little arrows for me. So lots of people like the arrows. So if you like to draw the arrows, then you should keep drawing the arrows. I'm okay with that. You don't have to do the notation I do, particularly as long as it's clear what you mean. Okay. Other questions? And we're going to talk more about that later. We haven't defined vectors. Vectors will be defined on next week on Tuesday. But I needed the formula and I was going to write it correctly. Okay. Are we good? Newtons, dynes, nothings. So that's a difference. Now, this is kind of what we mean by being consistent, is that when you put everything in SI to any physics formula we use, then the answer will come out in the correct SI unit for that quantity, generally as a derived unit. Okay. But if you also put in combinations of derived units, it comes out as a new correct combination of derived units or whatever. So it always works. Boone, yeah, that's very similar. That's the same kind of notation. I think the one with the R and the C for the set of reals and the set of complexes actually has a special name for it. But yeah, it's very similar. Very, very similar.